Let's talk about how to calculate yield to maturity with Python. We're going to start with discounting. Let's say you have a friend who promises $100 in 2 years in exchange for $95 today. Should you lend the money? You know that the safest investment available in the market is 2%. With this 2% of annual return, how much money do you need today to get $100 in 2 years? It turns out there is a formula for that, and it's called discounting. According to this formula, you need $96.12, which is higher than $95 that your friend is asking for, which means you should lend the money. The implementation of the discounting logic is very simple in Python. It's literally just this one line. And you can apply discounting to different periods. It could be decimal numbers. For instance, if you need to discount a future value in a year and a half, you can use decimal numbers. Let's think about the relationship between $96.12 and $100. If you have $96.12 today, you invested into a security with the annual rate of return of 2%. By the end of the year, you'll get $98.04. Then, if you invest $98.04 into the security that gives you the 2% annual return, by the end of the second year, you're going to get $100. And that gives you an understanding that compounding and discounting are processes that reflect the same dynamics. Compounding is like going forward in time, and discounting is going backward in time. By the way, the number of compounding periods matters. In these examples, you have the same annual return of 2%, but the present values are different because the more compounding periods you have, the stronger the effect of interest over time. So the present value in the second case, where we have two compounding periods of 1%, is lower. So we have a lower present value in the second case. Be aware of that. Okay. How can we find the present value of a cash flow? For instance, here we expect two payments of $100, and we need to find its present value. So we discount each payment of $100, and we sum it up. That's how we get the present value of a cash flow. And the implementation in Python is super simple. It's the same thing, but you add the sum function. Now let's talk about discount bonds. Discount bonds are bonds that are sold for less than their face value. For instance, if the market price of a bond is $900 and its face value is $1,000, this is a discount bond. They don't have coupon payments. We're focused on getting the profit from the difference between the face value and the market price. All right, two scenarios. In the first scenario, we need to find the present value, and that requires the exact same process as the formula for discounting. We've covered that. And the second scenario, you need to find the yield to maturity. You have the present value, you have the face value, and you have the maturity of 2 years, and you need to understand what the yield to maturity value is. And why is it important? Because the yield to maturity metric allows you to compare bonds of different maturities and prices. So for instance, here you have 3 types of bonds. They have different maturities and they have different face values. How do you know where you should invest? By the way, in trading platforms where you can buy bonds, you can often see fixed income offerings showing yield to maturities for different bonds of different maturities, and that allows you to compare them. All right, let's move on. So this is how we're going to implement the discount bond in Python. We have some methods that do some validation. Let's not dwell on this for too long. And we have the same discounting functionalities here that we discussed earlier. And here's the discount bond class. It has the getPV method and it has a getYTM method. YTM stands for yield to maturity. And we use the discounting functionality to get the present value, and we get yield to maturity by using the formula that I shared with you earlier. So here's an example. We have a discount bond with a face value of $110. The interest rate is 2%, the annual interest rate, and the maturity is 2 years. By the way, the face value of $110 is not typical. Typically, you see face values of $1,000. In this example, we got the present value of $105.73, and which means that if the bond price is $107, we should not buy it. It's not worth it. The second scenario, we are trying to find the yield to maturity. We have all the metrics, and we arrived at 5% of annual return, which means its yield is 5%. And if we compare it to something that offers us 4%, well, we should prefer the discount bond. And here's the example that I provided earlier, that I described earlier, where we had 3 types of bonds. They have different parameters, and it's really hard to compare them. With the yield to maturity metrics, we can do that. Look, we calculated yields for each type of bonds, and we concluded that the third bond is the best. Now let's talk about coupon bonds. Coupon bonds are similar to discount bonds in the sense that they also have a face value, but also they have coupons, regular coupons. To find a present value of a coupon bond, you need to find the present value of the face value and the present value of all the coupons. Here are the formulas. Quite straightforward, a little bit more complicated than with the discount bonds, but it's not very complicated. Well, the second scenario, we need to find the yield to maturity, and this is where things get more complicated, because there is no straightforward formula to find the yield to maturity of a coupon bond. Basically, what we have here is the function of an interest rate that we need to use iteratively to find the value that satisfies the equation. And this is the equation. So when the difference between these two components, the present value and this part on the left side equals 0, we found the yield to maturity. This is an iterative approach, and it might be computationally expensive. That's why there is the second formula, which is the estimated yield to maturity parameter. So this is the formula, and it's so much simpler, and the values that you get from two formulas are slightly different, and depending on whether you need a very accurate number or an estimated number, you can choose the formula. Okay, so this is how we're going to implement the bond class for the coupon bond. We do have some service methods. Let's not think about it. Let's not, spend too much time here. It's just some simple validation, and we have three major methods: get PV, which is the summation of the face value, present value, and the coupon's present value, and that is straightforward. Then the second method is get YTM, which provides the present value of, which implements the iterative approach that we discussed earlier. It's based on the Newton-Raphson method, which is this part, right? And we need to import optimized package from SciPy. And the second and the third method gives us the estimation of the yield to maturity, and it's a straightforward formula that you can see here. So these are our tests, unit tests. Let's run them. They give me good results. Everything corresponds to the expected values. You can see here that I provided some scenarios and I tested it with different maturities and parameters. Okay, let's look at the examples, at the different examples. So here I'm trying to find the present value of a coupon bond with the semi-annual frequency. And by running this, I get $951 for something that has this coupon rate and has this interest rate. In this case, I have no coupon payments because this is 0, and I have the maturity of 5 years. Let's take a different example. Let's take monthly maturities. You can implement it. You can find the yield to maturity by running this part. That will give you the yield to maturity of about 15%. Okay, there are more examples here, and you can find it in the description for this video. One more thing that I wanted to cover is the relationship, the inverse relationship between bond prices and interest rates. Here we generate bond prices with different interest rates, and you can see that the higher the interest rate, the lower the bond price is. And that will be it for today. Thank you.